Great, thanks, Grady, and thanks everyone for the invite and for coming. It's a pleasure to be here. So the talk I've prepared today, what I'm going to focus on is how we're developing graphs as a vehicle for machine learning physics and things along those lines. So the way I'm organizing this is hopefully I'd like to start just with some motivation about what graphs are. We all have some idea maybe, but maybe tied to the specific application of digital twins, which I'll explain what I mean by a digital twin. The bulk of the talk, though, what I'd like to talk about is this new framework that we have for basically identifying control volume analyses from data and extracting models from that. After, so that'll be the meat of the talk, but then toward the end, I'd like to give kind of a survey of some of the applications that we're applying these things to and where we think we've built what may be a foundation for doing automated scientific discovery in a few different applications. So first, what is a digital twin? When people say a digital twin, what they usually have in mind is that you have a physical asset, some system, and you have some model that can make a predictive simulation of that system. So in some sense, a traditional finite element simulation is this physical to digital arrow here. And then the idea is that the digital twin can feed back and inform the physical asset. So there's some notion of data assimilation and control and kind of like a closed loop system that you're building up. And very recently, so people have been talking about this idea for decades. Very recently with machine learning and reduced order models, it's actually feasible to do this kind of closed loop modeling and data assimilation in real time, at least on the time scales of the system that you're thinking about. And so the specific type of digital twins that we have in mind are what we call systems of systems. And so this is something where you have a hierarchy of models. So for example, at Sandia, I work on weather and climate sometimes. We have the E3SM model, which makes all the weather predictions that you watch on TV. And so we have multiple different codes, some for the atmosphere, some for ice, sea ice, land ice, the Earth model. These are all different big parallel codes that are all coupled together, but they're all communicating information across each of them. So what we're developing in our group are mathematical tools to kind of endow these things with certain properties, right? You want it to be physically realizable, conservative, stable, support all these kind of things. There's multimodal data coming from sensors all over these complex systems and so on. So it poses a rich ecosystem of mathematical problems. And so the center that Grady mentioned that I'll talk more about later is focused on climate, but we're developing these across a wide range of applications across Department of Energy. So systems of systems show up in mechanical assemblies, right? You could have a vehicle, you've got the suspension, the tires, the engine, the this, the that. In material sciences, it shows up in terms of pathways or mechanisms that lead to the formation of different, for example, thin films or other kind of material systems. In fusion power, we're very interested in this. People might have seen the really exciting result that came out of NIF recently, out of Department of Energy, achieving plasma, achieving fusion for the first time. And so there's a lot of engineering things about fusion that we care about. And one example is we're really interested in how the container where fusion is occurring, that material system at the molecular level, how that couples up to the magnetohydrodynamics or like the governing equations of the plasma, right? So we have multiple systems there that are talking to each other. And so it turns out a graph is a really natural way to talk about that. You can think of a node for a subsystem and an edge describing fluxes or information that are exchanged in between subsystems. So that's one reason why we want to work with graphs, because it naturally maps onto that kind of physical modeling. There's another version of why we want to use graphs, and the idea is to get away from correlation and toward causation in machine learning. So in machine learning, typically what you're learning is a way to parameterize and sample from a probability distribution. And so if you have two random events, call them A and B, the language of probability is insufficient to actually say what causes what, right? You could say you could describe this probability in terms of the event A conditioned on B, or the event B conditioned on A. They're both perfectly valid from a probabilistic perspective. And so to think about it, imagine you have a city altitudes and temperatures. I stole this from a presentation by Bernard Schroelkopf. So as maybe physics inclined people, you might be inclined to say, oh, the higher up you are, the bigger altitude, the more the temperature will drop, because temperature drops with altitude. But probabilistically, it's perfectly valid to say that temperature causes altitude. And that could give you explanations that look like, yeah, like if somebody wants to build a ski resort, they're going to do it on top of a mountain. If it's a beach resort, it's going to be on the ocean, right? So what we need is something extra in order to describe what implies what. And for scientific discovery, that's extremely important, right? Because what we want to say is, here's a huge data set, and we want to dig through it and say, oh, this is the scientific mechanism that's causing maybe this failure or this undesirable outcome. And now that we've identified that precursor to a rare event, then we can dispatch a strategy to take care of it. So it turns out that a graph in this setting is also a natural object for describing causality. And so it gets pretty philosophical, so I'm going to steer clear. If you dig into the literature, you'll find people arguing and getting all like very worked up. In our group, we just want to compute and we want to calculate things, and that's it. So this is a whole can of worms you could get into. But the idea is that a directed acyclic graph can describe these causal relationships. So if you have, in this case, we have random variables X and Y, the hypothesis behind the common cause principle is one way to think about it, from Reichenbach. And the idea is you assume that if X and Y are statistically dependent, there's a third random variable, like a latent hidden random variable Z, that's causally influencing everything. And so if you can identify what Z is, then these downstream effects, the X and Y, will be conditionally independent on Z. So the idea is this DAG encodes kind of like a chain of dependencies, which cause everything to become independent. So if you can fit a model that looks like that, then in this school of thought, then you've achieved some sort of a causal description. And so this is where graphs come in. We want to use graphs for that. And just to think about, how this usually looks, traditionally when people have tried to develop these causal graphs, these directed acyclic graphs, it's a brute force calculation, and it's inherently combinatorial and discrete, which means very, very expensive, and you can only consider very small systems. So the reason you want a directed acyclic graph means that you can't get circular reasoning. You can't get A causes B, causes C, causes A. You want it so that everything just goes downstream, if that makes sense. And so the idea behind the machine learning algorithms that we want to put together is, can we explore the space of DAGs without building every single one of them and saying, oh, this is the best one? We want more of a gradient-based way to search, in the same way that one would usually train a neural network. Okay, so what I'm going to focus on primarily in this talk is the physics model piece. And so especially at Sandia, it's a national laboratory. We have a lot of national security problems. A lot of these are high consequence engineering applications, and you can't just make a prediction. We actually have to guarantee that whatever, we have to guarantee that there's some trust built into those predictions that we're making, because lives are potentially at stake. So the kind of goals that we have are a means to replace a forward simulation. So think about like a Navier-Stokes solver or solid mechanics solver or something like that. But we need it to be 1,000 times faster because we have to do this in real time. So there's a lot of machine learning work that attempts to get that kind of speed up, but what they sacrifice is the guarantees you get along the way from traditional simulation. So we want to be able to guarantee accuracy, stability, and maybe most importantly from my perspective is physical structure preservation. So you want it to be energy momentum conserving, and maybe fancier physical abstractions for what you mean by that. And so once we have these kind of building blocks what we want to be able to do is glue them together to look at a system of system. Right? We want to be able to couple these cheap surrogates together, but guarantee that once we glue them together, again, it's not going to blow up. And again, it will remain physical. And we want to be able to do that in a way that supports uncertainty quantification, all these kind of things that people are interested in doing to query things. So before I dig into the math, I have this kind of little vignette that I think gets at the core of the idea. So when I was in undergrad, I was a math major, and my friends convinced me to pick up engineering double major, which was kind of foolish at the time. Like at the time, I didn't appreciate how much goes into engineering. So there's this class called statics. You design bridges, and I'd skipped a bunch of lectures. I showed up to the first exam, and I thought I could blow through it. And so what you have to do is you calculate the forces on this bridge. And foolishly, like a mathematician, I built this massive system of equations to work out the force in every single one of those beams. When it turns out the smart thing to do is you draw a control volume around the entire thing, and it works out to one single equation. So people would call that engineering judgment, the idea that you can set up a problem in just the right way so it becomes a simple problem. And people talk about things like parsimony, which is the idea like the most compact expression of a model to still be prescriptive. So that's basically all of engineering at the undergrad level, is learning how to draw control volumes very well and creatively, right? And so what we'd like to do is get machine learning to do that. It's something natural for a human, maybe not for AI. So it's going to get into some math and some weeds. So before I get there, I just want to start with the punchline so we can see what we're actually building. The idea is we're going to start with full order solutions. So something that comes from a high fidelity model or from experiment that give us full field data. So in this case, we have a velocity field corresponding to flow past a cylinder. And what we're going to identify are control volumes, so a partition of space, along with boundaries of those control volumes and a flux balance over those control volumes, all at the same time. So we're learning the geometry and the physics all at once. And so you can see it here, the data is the dashed lines, these are streamlines, and the learn model is the solid lines. What you can see in the background are these subdomains that are evolving. So each one of these colors is a different control volume. And so what we're ending up with at the end of training this model is something that optimally reproduces this data, but it expresses that in terms of fluxes, right? So you can see this circular control volume in the middle. What we have is a system of equations such that the fluxes, right? If you add up all the fluxes through these pieces around the outside, they all sum exactly to 0. So that's where we get all this structure preservation, maybe like fancier physical properties on top of it. Turns out there's a graph there. The nodes of the control volume, nodes are the control volumes, edges are boundaries in between control volumes. So we'll get to where that comes from. So the primary tool that we use is compatible spatial discretization of PDEs. And so at a hand wavy level, these are kind of like advanced discretizations, advanced finite element discretizations, with the core idea that you build up your approximation to differential operators, or if you're going to approximate div, grad, curl, stuff like that, you actually use the Stokes theorem. So like if you want to do a div, you work with a Gauss divergence theorem. And the simplest example of this would be a low order finite volume method, which people might be familiar with. So it turns out that by being faithful to the Gauss divergence theorem, you're being faithful to top topology and geometric structure that's hidden inside of these PDEs. And you get a bunch of downstream properties that follow as a result. So people call this mimetic or physics compatible discretizations. And in particular for electromagnetism and a lot of the problems that we care about at Sandia, just in the forward simulation world, like no machine learning or anything like that, this has been crucial. So when, you've heard about fusion stuff in the news, fusion simulation was not possible till about like 20, 30 years ago when they started incorporating these types of ideas. It's controversial. You could say it started earlier than that. But just to say, this is something with a long history, and it's very, very impactful on the simulation side. There's two kind of broad classes. I don't want to get into the details too much. I'm just giving the lay of the land. There's two classes and methods. Some of you may have heard of these. So in one case, there's a finite volume scheme, base scheme. And so that would be something, people call this a discrete exterior calculus. But the idea there is this would be like your low order finite volume scheme, where your degrees of freedom are fluxes associated with faces of a cell. Your divergence you get by summing up the fluxes and so on. So in that case, you're working kind of with a discrete algebraic system. On the other end, you have the finite element exterior calculus. And the idea there is you build up finite element spaces which interpolate phase flux degrees of freedom. So it's kind of like a finite volume or a finite element perspective. Both of them are linked to the Gauss divergence theorem under the hood. So our work, we started on the left with this DDEC formulation. We moved toward Fick toward the end. I'm kind of going to step through the highlights and try to keep the math to a minimum and just give the overall story. So the first thing to understand is how calculus works on a graph. And the key takeaway, there will be some notation to slog through. If I figured it out, I'm sure you guys can figure it out. At the core, it's just linear algebra. But the key takeaway is that everything you know about vector calculus, it maps onto a graph in the exact same way. Div, grad, curl, everything for multivariate calc. There's a graph version of that. Okay, so I'll start with some definitions. So first, a k-clique is an ordered collection of nodes. So a node of a graph would be an example of a one clique, an edge would be an example of a two clique. You can have higher order cliques, right? Like a triangle and higher order cycles that kind of loop around an arbitrary number of nodes, k nodes, right? But it has some orientation associated with it, like it's clockwise if you look at a triangle, for example. Then there's something called a graph co-boundary operator, and that's something that maps from a k-clique to a k+1 clique. It's defined through this kind of abstract formula, but this is an example of div, grad, and curl. If you evaluate this formula, you're reduced with something like this. And so when I say it maps from a k-clique to k+1 clique, right, a graph gradient, which is shown here, that maps from two nodal values and it gives you an edge value. And similar, this would be the graph curl. You take something that lives on edges and it maps to a three clique. So once you have that, you can build what's called a combinatorial Hodge Laplacian. This is a graph Laplacian. A graph Laplacian, if you're familiar with that, would be one example of this. But that would just be a graph divergence of a graph gradient, like what you would, like the Laplacian that you're familiar with from vector calculus. And the most important thing of all is this exact sequence property, which is if you take the curl of a gradient, it's exactly equal to 0, the same way it is in vector calculus. Same thing about the divergence of a curl and so on. So this exact sequence property is the most important thing, and this is where all of the physical structure kind of like falls out of as you go through the theory. So what I've shown here, this is an object called a de Rham complex, which has a scary name, but really all it is a mapping of all of these differential operators, right? So this would be a one clique, a two clique, a three clique. Along the top, you have these co-boundary operators. So this would be like a graph gradient, a graph curl, a graph divergence, right? And the way to think about these are just matrices, right? A gradient is something that takes values on nodes to values on edges. And then along the bottom, you have the transpose of those guys, right? You have the gradient transpose, the curl transpose. And so the transpose operators, these are adjoints to these differential things. So the adjoint of a gradient is a divergence. And so the way you would get a Laplacian, right, is you would take the gradient and then you would come back here, right? That would take you from nodes to edges and then back to nodes. And so this is just a way of organizing these operators and keeping track of everything. There's nothing fancy here. There's just one other property. There's only one other property, which is that it has this exact sequence property built in. So if you go from here to here, and then here to here, that amounts to taking the curl of the gradient, and that's equal to 0. Right? So you go along 2 edges, that's equal to 0. If you go along the bottom, you have the same property. That would be the div of curl is equal to 0. So the key idea about all the machine learning stuff is we take that graph calculus and we introduce machine learnable information that kind of rides on top. So now if we want to take a machine learned gradient, which we'll call D0 here, right? So if we're looking at this guy, the way we do that is we apply our learnable operator, apply the graph gradient, and then come back. So this is what people would call a commuting diagram. This is something where you can follow any paths along here, and it will preserve this exact sequence property. So the idea is if we want the curl of the gradient to be equal to 0, right? If we go from here to here, here to here, that's the same as if we went over to the graph calculus and then came back, right? And we have an exact sequence buried in this piece, right? So that's the idea. So we're just kind of parameterizing, we're fleshing out the graph calculus in a way that we can fit some data to some of these matrices. So it turns out that once you have these building blocks, it's not important to understand this math or what it means. The important thing is that all of the standard results from traditional finite element analysis apply here. So we get this exact sequence property. We get a Hodge decomposition, right? You can write a velocity field in terms of a gradient potential plus the curl of a vector potential. You get a Poincare inequality. You can build up a Lax-Milgram stability theory. These are all the things in like an introductory graduate level finite element course that you can do with finite element spaces. You can do the same thing here, which you, in general, you can't do analysis for machine learned PDE models, or if you can, it's extremely tortuous. It's very straightforward here. Works the same way as you would teach it to someone fresh out of undergrad. And so the way you learn models in this framework is you pose a conservation law. So in this case, I'm going to say, all right, I've got the divergence of some fluxes is equal to the sources. I'm going to assume those fluxes look like, this is like grad phi, this is a gradient flux, plus a non-linear black box flux, right? So this is something like a deep neural network that can capture any nonlinear relationship. And the idea is, you know, you have a divergence of a gradient, that's a diffusion. So that's a nice stable thing that you can prove a lot about. And then you have a nonlinear perturbation to that. And so that's going to let you prove a lot of things in the same way. It's like adding artificial viscosity, if you're familiar with that trick. So the idea now is if we have a graph, if we have data, for example, we have a high fidelity solution, we partition space, we identify subdomains with nodes, faces with edges. Now we can train a model to reproduce this high fidelity data subject to this constraint. So we say, give me a model that when you solve it, it'll reproduce the data, but it will be conservative, right? Like it's built into the structure. So mathematically, you can write this out. This says the exact same thing. You assume you have fluxes where you have a diffusion flux plus a nonlinearity. But this isn't just for like sum of fluxes, divergence type conservation laws. In electromagnetism, you get conservation of circulations. Same thing in fluid mechanics if you talk about vorticity. There are different classes of conservation laws that this abstract framework maps onto. And the important thing is that you always end up with this story. You have a nice bilinear form, a nice elliptic diffusion looking thing that you can prove a lot about, plus some black box thing that's meant to catch all of the data, all of the nonlinear relationships in the data, but we don't need to actually know how to write down that governing equation, right? When you discretize a PDE, you assume you actually know the equations. In this case, we're going to learn them from the data. And so what this means is, even if you have very, very sparse data, you have like one data point, you can only run one experiment, we can guarantee that it will be conservative. And it turns out that you can guarantee it'll be solvable. So if the nonlinearity is small enough relative to this diffusion thing, right? That means that you can impose this as an equality constraint when you're training a model. Okay, so that's the idea with the graphic theory calculus. The idea is that if you have a network, you can hang a model on top of it. The drawback to that is you need a network. You need some graph that you're going to hang that data on top of. So when somebody hands you a graph, it's kind of like meshing in finite element simulation. When somebody hands you a graph, we know what to do with it, but where does that graph come from? So there's plenty of applications that we work on, like machine learning models for electrical circuits, hydraulic networks, where there is this kind of natural network already built into the problem. But for the actual problems that we probably care the most about, there is no obvious network. Somebody just gives you a velocity field, which we would call full field data. So that could be like PIV or DIC. Those are two experimental techniques for extracting a velocity field or a deformation field from a fluid or a solid flow. It could also be if somebody hands you like DNS, like a high fidelity turbulence simulation, right? Like there's no graph there. It's just a vector field. Okay, so what we're going to do, all that stuff at the beginning, I talked about control volumes. We want to actually pull out a graph. We're going to discover that graph from the data. So we're going to need another definition. This is something called a partition of unity. And so a partition of unity is a collection of functions that are positive and they sum to 1. And we're used to thinking about something like indicator functions on cells of a mesh as one example of a partition of unity. But that would be a disjoint partition of unity. The support of these functions wouldn't overlap. But in general, they can be diffuse, they can blend into each other. In the mesh-free community, people have thought about POUs in this way for a very long time. In machine learning, there's a different partition of unity that people usually use for saying, this is the cat part of space and this is the dog part of space, where you have a neural network composed with a softmax function. This is a machine learnable partition of unity that gives the same effect. It's a means of splitting up space so that you can work locally in different parts of space. It's kind of a divide and conquer strategy. So we've used these just to give a sense of, I give a whole talk on this in itself. We've done a lot of work where we do piecewise polynomial approximation. Grady, you might find this interesting from the RBF POU style thing. The idea is each partition gets its own polynomial fit. And during training, you're finding POUs and then immediately solving a least squares problem. So you get an optimal polynomial representation of data, and then you're pushing the partitions around. So in this case, I have a video showing, say you want to approximate this piecewise quadratic function. A human, you just have to mesh that. You need to make the edges of the elements match the discontinuity if you want to get that right. In this setting, basically, these are partitions of unity, and you can see that it snaps onto those, right? So without telling it anything, it's just hunting for a good approximation of the data. It finds that. So as a mesh-free person, this was what I always hoped mesh-free methods would do. that it could get away from, you don't need to make a mesh. It will find the mesh for you. There's a lot of other details there. Maybe the most important thing is that a traditional neural network, doesn't matter how big of a network, how wide, how deep, you'll get 1% error out of it. And that's been a big drawback for using this in scientific computing applications. But with this POUnet stuff, you can get spectral convergence and the kind of stuff that you expect and need for scientific computing. Okay, so our objective is to repurpose this partition of unity stuff in order to identify control volumes. And so this is the hand-wavy explanation about how we cook this up. It gets technical, so you can just remember this slide, and that's 90% of the story. So the idea is a partition of unity generalizes a cell. So if we want a conservative divergence operator, what we really need to do is define what we mean by a boundary of the cell. And so in this video up here, I have a cartoon where the two red lines are two different partitions of unity, and I'm going to sharpen them up so they approach an indicator function partition of unity. And so this blue line in between is this notion of a boundary that we're hunting for. So as you go to two indicator functions next to each other, we would think of the boundary of those as maybe a Dirac mass, right? That's the sort of thing that we're trying to figure out, but we don't want it to be sharp. We want it to be out here. So it's machine learnable. Everything's differentiable. And this is all just hidden in the weights and biases of a neural network. So it turns out this object, this blue line, is something called a Whitney form, and it showed up all over the place in scientific computing. I'll probably go through this quickly because got a late start and I don't want to get too bogged down in the math. But the way Whitney forms are usually constructed is you have a finite element. You imagine you have vertex degrees of freedom, and you build up something called barycentric coordinates. So these would be like shape functions, like a normal finite element method, but they have this partition of unity property. So that, like, this is the key. This is the secret sauce. So we're stealing the usual Whitney form construction based on barycentric coordinates, and we're replacing this with a different partition of unity. That's the whole idea behind this. And so these would be like your usual P1 Lagrange interpolant piecewise linear finite elements, like the first finite element space you would usually work with. Those are barycentric coordinates. Those are an example of barycentric coordinates. So the idea with a Whitney form is that it just has this definition. It's a scary formula. It's defined abstractly, but at the end of the day, you can define a different way to define the finite element space is you take the nodal degrees of freedom for the lowest order Whitney forms. So this would be the first order Whitney forms. And you find on each element the interpolant of this space. These two descriptions are equivalent. And then to get the next order Whitney forms up, you take as degrees of freedom the tangential component of the vector field integrated against edges of your mesh, and you interpolate this finite element space. The next one's up, it's the face fluxes. It's u dot the normals integrated over face areas. So what this reduces to is this expression. So if you start with barycentric coordinates on the lowest order, this formula tells you just, take some gradients and add them together in certain ways, and then you'll end up with this. So the reason this is defined in such a complicated mathematical way is it's meant to work on an arbitrary manifold. So like if you're on the surface of a sphere or you're doing relativity, you're doing something complicated, this all goes through in the exact same way. The important thing is that this will be exactly faithful to the Stokes theorem. So to make it clear what I mean by that, if you start with these Whitney forms, the lowest order Whitney form, and say you take the gradient of that along an edge, you can apply the fundamental theorem of calculus to figure out what the gradient of phi is on that edge, right? Grad phi dot dl along this edge is the difference of the values at the endpoints. But this is exactly the degrees of freedom for the next Whitney form up, and so on. So now if you take a curl, you'll get, you get fluxes that map to a divergence and so on. So these are the reason these are cooked up. It's a long discussion to get into the actual theory behind it, but it's set up so that the derivative of one will exactly map into the other one, and that's how you exactly preserve all these conservation relationships and so on. And because those are exact, that's where divergence of curl is equal to 0, because a curl and a divergence are both treated exactly. So it's a little bit hand wavy, but hopefully that gives the gist of it. So it turns out we just stumbled into the fact that Whitney forms correspond to this. What we were looking for was, we're motivated by a traditional low order finite volume scheme shown here. We were thinking, okay, we've got a POU, which is something like a volume, and we're hunting for something that's like an area over here. So what we did was we integrated the POU against div u and integrated by parts. And then it turns out that you can massage, these are just properties of partitions of unity, right? You can multiply this expression right here by 1, and apply the identity, the one's equal to the sum of the POUs. You can add 0 to it. And now you're left with this expression here, which is anti-symmetric in I and J, the same way that an area would be, it has a normal orientation on it. And so this turns out to be the exact same formula that showed up here. Completely stumbled into it by surprise. We reinvented something that somebody came up with like 100 years ago in classical modern physics. So it turns out that you can repeat the process. So you can just do it by induction. So now that you know this one, you do Leibniz rule again, but now it would be psi ij here and a curl here, right? But you kind of just follow your nose and do the same process. This looks like gibberish to me. Sure, it looks like gibberish to anyone who's never done exterior calculus before, so don't stress. But the point is that you can do this on an arbitrary manifold. So you could do this, for example, embedded inside of an autoencoder. You could do this on the surface of the Earth. You could do it in all those kind of contexts. All of the structure preservation goes through. So there's a really deep connection here, right? So we've defined div, grad, and curl in terms of summing over these generalized fluxes. It turns out that those are related to the graph div, grad, and curl that I mentioned before. There's an identity that you can prove. I'm not going to prove it. But it comes through the mass matrix associated with these Whitney forms, right? So that the mass matrix associated with the Whitney forms is telling you how to weight the graph. And it's kind of imposing the topology and the boundaries on the fully connected graph. And it's telling you, actually, this is connected to that through the boundary of the POU. So there's a really deep connection there. And there's a lot of really interesting papers from the last like 50 years, if you want to get into the pure math side of it. But I'm going to try and quickly get to how you actually use this stuff. So what we want to do is build a finite element space now. There's some extra requirements. You need to be able to integrate this. You want to perform quadrature if you're going to use this to solve a PDE. So we put together a specific partition of unity, which is you start with tensor product B-splines, and you take convex combinations of them. So it turns out that convex combinations of a partition of unity is, again, a partition of unity. And we make this convex combination in tensor machine learnable. So basically what you do is you have this Cartesian grid, and then you're clumping it up. You're grouping it together, and you say, okay, so you've got like n by n nodes. Give me like the 10 best groupings of them, which will partition space. And so shown here in this column are the entries of this trainable tensor. Shown here are the shape functions that they correspond to. There's some tricks that you do with Dirichlet boundary conditions and lifting at the boundary, so you can actually impose boundary conditions downstream. It's a technicality. The important thing, right, is that this pops out finite element spaces that are designed to integrate in a weak form of a PDE. So shown here now, those are first order Whitney forms, the partitions of space. Now these are the shape functions that correspond to the boundaries between those partitions of space. And so along the top and along the side here, this is a set of POUs, and shown in the middle is the boundary that those two POUs share, right? So for example, this is the boundary in between this partition and that partition. And you can see that they're anti-symmetric, right? When you flip your perspective, boundary of I or boundary of J for face Fij, and the boundary of a partition with itself is equal to 0. So this is the construction. It's a parameterized finite element space that will pop up. Usually we would build these by hand. Instead, we're going to kind of machine learn them. So the idea, in this case, we're just going to learn a diffusion problem. Just to keep it simple. You could do all the other stuff I was talking about before about learning a nonlinear flux, but just to keep it bare bones, say you want to learn a finite element space that is constrained to satisfy a diffusion equation. So this is equivalent to saying, give me a set of control volumes. We know it's a diffusion flux in between every phase space, but what are the control, like what's the finite element space that would optimally describe that in as few shape functions as possible. And this is what it looks like when you train. These are just some like manufactured solutions so you can get a sense. You can see as you take more B-splines, it converges like a normal finite element method. The interesting thing is if you look at problems like where you have discontinuities in conductivity, for example. So this 5-strip test problem is kind of a benchmark in mimetic finite element simulations, because the idea is that you have 5 strips. Each one has a different diffusivity, kappa 1, kappa 2, and so on, all the way down. And you're imposing a unit pressure drop across the whole thing. So by mass conservation in the boundary between the strips, the jump in the flux has to be equal to 0, right? Like it has to hand off the correct amount of flux from one subdomain to another. And basically what this benchmark is showing is that it discovers these strips on its own. We don't tell it where the strips are, we just tell it here's a pressure field. And then it pulls out, oh, these are physically interpretable strips where the conductivity is different and so on. So where we're using this at Sandia, one thing that I work on is lithium-ion batteries. You can do CT scans to actually look at the microstructure of a real battery. And we have very expensive, like super non-trivial ways of automating mesh generation. So you start with a voxelized CT scan, you hand it to the machine, the machine builds a TEP mesh for that. And it's an absolutely massive mesh. So this toy 2D problem is 6 million finite elements, but we're easily talking about like billions or even hundreds of billions if we're talking about an actual battery. And so the important thing about this is, so we can afford to do a handful of those. We can't, this is the digital twin thing where we can't actually build it up, right? But the important thing is that this describes the transport pathways through the microstructure, like where electricity is actually flowing. And what we care about is these will get fractured when they get damaged. And it's kind of like an accident on the highway. It reroutes everything down a separate path. So it's a really challenging multi-scale problem. And so we can compress this for this toy problem, which is like 6 million finite elements. We can get 8 data-driven finite elements that maintains an error below 1%, like in the engineering norm. But most importantly, it gets the conservation relationships, right? Which is what you need in order to get these transport pathways. We're doing more complicated versions of this for semiconductor physics. But all these kind of things where you have a submodel, this is the digital twin thing I was talking about, where you have a submodel, you want to punch out the expensive inner part and then see how it interacts with the network of other things. Like, so this is one transistor, you got a billion of these in your cell phone. This is 100,000 finite element mesh, right? So they can afford to do one of these at a time. We could extract our data-driven model and then stitch a billion of those together. That is tractable. Right? So that, just to give a flavor of how these things work. I'll make sure I leave some time for questions. I'll just blow through this. We have this other project that I'm running where totally change of pace. This is actually like high throughput. Think of robots fabricating thin films and then characterizing them, testing how strong they are, and so on. For these problems, really what I want to show was where we can embed these data-driven models to do kind of like beyond forward simulation, beyond kind of traditional scientific computing. Right. So the idea behind this project is we have these machines where it's kind of like an assembly line. You can print many, many different variations of a design at the molecular level, like you crank the pressure up a teeny bit, change the chemistry, change this, that. And you use that to crank through 10,000 different parameters that correspond to a given material fabrication. And so there's a lot of different material systems. We look at electroplating, it's called physical vapor deposition, 3D printing, like metal additive 3D printing or laser powder bed fusion. And so the idea is that now that the experimentalists can use robotics to generate a large data set, can we machine learn through those things? So, this could be a whole talk on its own. But the point is that we put together this deep learning architecture. It's a variational inference framework for combining all of, people call it multimodal data, all the different kind of experiments, material characterizations that look totally different, microscopy, x-rays, and so on. We combine all of them into a latent space, like a low dimensional latent space, where we model them as a Gaussian mixture. And then we decode them. Some things like an X-ray, you have to do black box machine learning on, there's no physics you can do. But some things like electroplating, there's bath chemistry. We're embedding these data-driven models in here, right? So we're hoping that the physics will reveal patterns in the data. So in this case, these are two different 3D printed lattices, a population of different ones. We're doing uniaxial extension tests. I'll start it over. So each black dot corresponds to an image of the lattice as well as a stress strain curve for that lattice. And during training, you can see it kind of like swapping data points back and forth between clusters. But you can see a physical model here, in this case for solid mechanics, helps it figure out what the two different populations are. And then that helps it sort out like the image of what these two different subpopulations look like. So there's a lot of examples where we're doing that. Metal additive, we have models for heat transfer within the melt pool, laser melt pool. For electrochemistry, we have models for the electrochemical transport in the bath as it deposits ions onto a gold film or a copper film. This has been picked up at Stanford. They have a project where they're using it for laser ignition of rocket engines. And they're trying to figure out like why their rocket either ignites or doesn't ignite. So across all of these like black box data-driven models, very hard to like get physics into, right? But now that you have this cheap surrogate that you can hook in, now you can, it's a way to bake some physics in there. So maybe I'll leave it at that. I'll say one thing about this center, this new center that we have, because this is really where I didn't get to run out of time to talk about causality. But the idea behind this for climate is you want to identify these kind of reduced surrogates for climate models. And then you want to identify little blips. Like, so say you have data from like a wildfire in the Earth model, you want to identify that as a precursor to a hurricane in the atmosphere model, right? So it's really about the question of, once you can make PDE simulation essentially free, like now there's this whole other class of problems that, previously we just always like shut our brain off and thought it was too expensive to think about. So maybe I'll stop there and take some questions if there are any.